Every year, thousands of hours of video get uploaded, claiming to show what governments are hiding at the bottom of the world. Leaked drone footage, restricted zones, suppressed discoveries. The content is convincing enough that millions of people watch it, share it, and believe it. Almost none of it is real. What is real is more extraordinary than anything those videos claim to show. Underneath the Antarctic ice sheet, there are 231 hidden lakes, 138 volcanoes nobody knew existed, an entire mountain range buried under 4 kilometers of ice, and living organisms that have been sealed in complete darkness for thousands of years. The largest military force America ever sent anywhere went to Antarctica in 1946 and came back with classified orders nobody talked about for decades. A particle physics detector built inside the ice itself has been catching signals from exploding stars billions of light years away. And the glacier sitting at the continent's western edge is doing something that will directly affect the survival of every coastal city on Earth. None of this is a conspiracy. All of it is documented, verified, and hiding in plain sight. Section 1. The real restricted zone. What the Antarctic Treaty actually prohibits and why. On December 1st, 1959, 12 countries sat down in Washington, D.C. and signed a document that would determine who controls the most remote place on Earth. Not just who controls it, but who is allowed to enter it, what they are allowed to do there, and what happens when someone breaks the rules. That document is the Antarctic Treaty. It came into force on June 23, 1961, and it remains the legal foundation for everything that happens on the continent to this day. The 12 original signatories were Argentina, Australia, Belgium, Chile, France, Japan, New Zealand, Norway, South Africa, the Soviet Union, the United Kingdom, and the United States. These were the countries that had sent research teams to Antarctica during the International Geophysical Year of 1957 and 1958, an 18-month global science project where nations that were otherwise pointing nuclear weapons at each other agreed to share data. By the end of it, everyone involved concluded the cooperation had been worth doing. The treaty that followed was the attempt to make that cooperation permanent. Today, 58 nations have signed it. The core rules of the treaty are straightforward. Antarctica shall be used for peaceful purposes only. No military bases. No military exercises. No weapons testing of any kind, including nuclear weapons. No nuclear waste disposal. No economic exploitation of the continent's resources. No new territorial claims, and no expansion of existing ones. Any nation that has signed the treaty has the right to send observers into Antarctica at any time, with complete freedom of access to every station, installation, and piece of equipment on the continent. There are no exceptions to that inspection right. Every signatory agreed to it. What the treaty does allow is equally important. Military personnel and military equipment can be used in Antarctica, but only for scientific research or logistical support. The United States has used military aircraft and personnel to supply its McMurdo Station for decades. New Zealand's Air Force has run regular patrol flights from Pegasus Airfield near McMurdo since 2006. None of that violates the treaty, because none of it involves combat capability, territorial assertion, or weapon systems. Now here is where the restricted zone part becomes real and specific. Under the broader Antarctic Treaty System, which includes the original treaty plus later protocols and agreements, large portions of Antarctica carry formal access restrictions. Antarctic Specially Protected Areas, known as ASPAs, are zones where even entering without advance authorization from a national competent authority is a legal violation. These areas exist to protect specific ecosystems, scientific research sites, geological formations, and historic locations. Researchers who want to enter an ASPA must submit a permit application and receive approval before they go anywhere near the boundary. Antarctic Specially Managed Areas, known as ASMAs, are broader zones where multiple activities are coordinated under a management plan, and where specific activities are permitted or prohibited depending on that plan. Flying a drone over either type of area without authorization is explicitly prohibited. On top of those categories, no UAV, meaning no drone, commercial or otherwise, can fly near concentrations of wildlife, over historic sites and monuments, or within range of a scientific station without the explicit permission of the base commander. The regulations are not vague. They were formalized into specific UAV guidance that has been in place since at least 2019. The practical result is that large portions of Antarctica are legally off-limits to independent aerial surveillance. That legal framework matters because of what happens when it gets ignored. In late June 2025, a 19-year-old pilot named Ethan Guo filed a flight plan stating he would circle Punta Arenas in Chile. Instead, he flew his Cessna to King George Island in Antarctica and landed without authorization. Guo had been attempting to become the youngest person to fly solo to all 7 continents, raising money for childhood cancer research, a journey he had started in May 2024. By landing where he was not supposed to, he triggered international aviation protocols for unauthorized Antarctic airspace entry. Chilean authorities arrested him immediately. A Chilean court ordered a 90-day investigation. He remained in custody under restrictions from both Chile and the Antarctic Treaty governance structure. No alien bases were found. No secret discoveries were suppressed. A young pilot made an unauthorized detour, and the international legal system that governs Antarctica responded exactly as it was designed to. Understanding why that legal system was built the way it was requires going back further than 1959. Before the treaty, Antarctica was not peaceful. Multiple nations had planted flags, established outposts, and made competing territorial claims on the same patches of ice and rock. Argentina, Chile, and the United Kingdom all claimed overlapping sections of the Antarctic Peninsula. Those overlapping claims generated real friction. In February 1952, at Hope Bay on the tip of the peninsula, Argentine military forces fired warning shots at a group of British personnel who were attempting to rebuild the station. The British response was to dispatch a warship, which landed Marines at the scene on February 4th. This was not a conspiracy. It was a documented armed confrontation between 2 NATO-adjacent nations over a piece of frozen coastline at the bottom of the world. The year before that incident, in 1949, Argentina, Chile, and the United Kingdom had signed the Tripartite Naval Declaration, committing all 3 governments not to send warships south of the 60th parallel south. That agreement was renewed annually until 1961, when the Antarctic Treaty itself made it unnecessary. The treaty didn't resolve the territorial claims. It froze them. No one gave up their assertion. No one had to recognize anyone else's assertion. The treaty simply required all parties to behave as though the claims did not exist for the duration of its operation, which is indefinite. 7 countries still hold those frozen territorial claims: Argentina, Australia, Chile, France, New Zealand, Norway, and the United Kingdom. The United States never made a formal claim, though it has reserved the right to do so. The Soviet Union likewise never claimed territory, but reserved the right. Russia, as the Soviet Union's successor, maintains that position. When the treaty was designed, the United States and Soviet Union were the 2 powers most invested in making sure neither side could use Antarctica as a Cold War staging ground. Their diplomatic coordination was what made the 1959 agreement possible at all. What the treaty created, in practical terms, is a continent managed by committee. The Antarctic Treaty Consultative Meetings, ATCMs, are the governing body where member nations make decisions about everything from tourism management to environmental protection to airspace rules. The 46th ATCM was held in Kochi, India, in May 2024. Agenda items included biological prospecting, safety protocols, tourism regulation, climate change response, and inspection procedures. These meetings are where the restricted zones get defined, enforced, and updated. In February 2024, the commander of Iran's regular navy publicly stated that Iran claims property rights in Antarctica, plans to raise the Iranian flag there, and is preparing to launch both scientific and military projects on the continent. Iran is not a party to the Antarctic Treaty. That statement landed in an ATCM context as a direct challenge to the treaty's authority, because Iran is under no legal obligation to honor restrictions it never agreed to. How that plays out over the coming years is genuinely unclear. The inspection system built into Article 7 of the treaty is one of the most unusual features of any international agreement ever written. Every signatory nation with consultative status has the right to designate observers with complete freedom of access at any time to any or all areas of Antarctica. Every station, every installation, every piece of equipment, every ship and aircraft at points of discharging or embarking cargo or personnel. No advance notice is required, No permission is needed from the country operating the station. If the United States wanted to walk into Russia's Vostok station tomorrow and look around, the treaty gives it that right. Russia could walk into McMurdo Station with the same legal authority. This is the only arms control and inspection framework in the world that works on those terms. What does all of this mean for the idea of a restricted zone in the conspiracy sense? Some area where governments are hiding discoveries and shooting down drones? The treaty explicitly prohibits such a setup. Every area of Antarctica is legally open to inspection by any consultative party at any time. The restricted zones that exist, the ASPAs and ASMAs, are environmental and scientific protection zones with documented purposes, published boundary coordinates, and permit systems accessible to researchers from any member nation. The governance structure is not secret. The meeting minutes of every ATCM are publicly available. The list of every ASPA and ASMA, their boundaries, and their management plans are published by the Antarctic Treaty Secretariat in Buenos Aires. What the treaty does create is a continent where 58 nations have agreed to prioritize science and environmental protection over territorial competition and resource extraction. That agreement has held for over 60 years, an extraordinary achievement given what the continent was starting to look like before 1959. The restrictions that exist are real. They are just not hiding what most people assume they are hiding. But there is a reason those restrictions matter more now than they ever have before. Beneath the ice that all of these nations are so carefully regulating access to, something is happening that the treaty's original authors could not have anticipated. Something that the people who operate the monitoring satellites and drill the ice cores are watching with increasing urgency. The subglacial world hidden under kilometers of Antarctic ice is not static. It is moving. And some of what it is doing has direct consequences for every coastal city on Earth. Section 2. Operation High Jump, the largest military force America ever sent to Antarctica, and what it was actually looking for. On August 26, 1946, Admiral Chester Nimitz stood before reporters and announced that the United States Navy was sending the largest military expedition in history to the bottom of the world. The operation had a name, High Jump. The force assembling for it was extraordinary: 4,700 men, 13 ships, and 33 aircraft. For context, that is roughly the same number of personnel the United States used in certain Pacific Island campaigns during the war that had ended barely a year earlier. They were not going to fight anyone, officially. The operation was formally titled the United States Navy Antarctic Developments Program, 1946 to 1947. It was organized by Rear Admiral Richard E. Byrd, the most famous Antarctic explorer in American history, who by that point had already made 3 previous expeditions to the continent between 1928 and 1941. Field command went to Rear Admiral Richard H. Cruzen. Byrd was technically the officer in charge of the task force's scientific and research work, operating from the base camp rather than commanding the fleet. The distinction matters because it tells you something about how the operation was structured. It had a military commander and a scientific figurehead, and the priorities of those two roles did not always point in the same direction. At a press conference in November 1946, Byrd described the mission in terms that sounded straightforward. It was, he said, primarily a military operation to train naval personnel and test ships, aircraft, and the newly developed helicopters under extreme cold conditions. A secondary goal was to expand knowledge of the region's geography, weather patterns, geology, and electromagnetic conditions. Establishing and maintaining air bases in polar environments was a specific technical objective. All of that was true. None of it was the whole story. Historian Diane Olson Bellinger, speaking to Smithsonian Magazine in 2007, confirmed what the declassified record shows. The Navy had also been given classified orders to establish a territorial claim for the United States in Antarctica. This was 1946. The Cold War had begun. The Soviet Union was already signaling interest in the continent. American officials were acutely aware that if the Soviets established a presence there before the United States locked down a formal claim, the strategic picture in the far south would shift in ways that were difficult to predict. Byrd himself had been making the case to Navy Secretary James Forrestal and Admiral Nimitz for years that the United States needed a permanent foothold in Antarctica. Congress approved the funding. The money came with a clear understanding that this was a Navy operation with naval interests taking priority over scientific. The task force sailed in 3 groups: Central, Eastern, and Western, leaving various ports on December 2, 1946. The Central Group, which included the flagship USS Mount Olympus and the icebreaker USS Northwind, made its way through the pack ice toward the Bay of Whales on the Ross Ice Shelf. Norwegian trawlers operating nearby reported the ice that season was the heaviest in more than 40 years. The Northwind was essential. Without an icebreaker leading the way, a standard naval vessel hitting that pack ice would have been opened like a can. The Central Group reached its destination on January 15, 1947, and immediately began constructing a temporary base designated Little America 4, built near the location of 3 previous Byrd expedition bases. The helicopters that Byrd had mentioned in his press conference turned out to be one of the most consequential elements of the entire operation. These were Sikorsky models, relatively new technology in 1946, and they were used primarily for scouting routes through the ice pack ahead of the ships. Without aerial reconnaissance from the helicopters, the Central Group would likely have arrived at the Bay of Whales too late in the season to establish the base at all. The ice would have driven them back before they could even begin setting up. 2 helicopters were lost during the operation. In one incident, a helicopter returning from a reconnaissance mission plunged into the sea after ice accumulated on the rotor blades. The crew was rescued. On December 30, 1946, before the Central Group had even reached its destination, tragedy struck the Eastern Group operating in the Bellingshausen Sea. A Martin PBM-5 flying boat, designated George 1, crashed on Thurston Island. 3 crew members were killed. 6 others survived and were stranded on the ice for 13 days before rescue aircraft could reach them. The conditions that killed those men: unpredictable Antarctic weather, terrain that offered no emergency landing options, distances that made rapid rescue almost impossible, would define the character of the entire operation that followed. On January 21, 1947, Seaman Vance N. Woodall died on the Ross Ice Shelf. He was killed in what the official record describes as a ship unloading accident, crushed by roller equipment being used to flatten the ice for an airstrip. His crewmate Edward Beardsley later described Woodall's death as his worst memory from the entire expedition. These were the only confirmed fatalities of Operation High Jump: 4 men dead on a mission whose public rationale was training and scientific study. The aerial photography work was the operation's most tangible achievement. Aircraft completed 28 photographic flights, capturing more than 70,000 photographs over approximately 1.5 million square miles of Antarctic territory. Byrd noted afterward that the hope was to have sufficient material to construct a detailed map of the entire continent. That goal was not fully achieved. The photographs turned out to have a significant technical flaw. The ground control points needed to make the aerial photos accurately mappable were inadequate. A follow-up operation, Operation Windmill, was sent to Antarctica in 1947 to 1948 specifically to correct that problem by establishing proper ground reference points for the high jump photographs. Beyond the photography, the geological collection work produced something unexpected: evidence of a large coal deposit in the Antarctic interior. Coal is a fossil fuel that forms from compressed ancient organic material: forests, swamps, plant life. Finding coal in Antarctica confirmed what geologists had theorized but not yet proven from physical samples: that this frozen continent had once been warm enough to support dense vegetation. The coal data went into American strategic planning files, contributing to the growing picture of what resources the continent might hold. Despite all of this, many of the men who served on Operation High Jump came away feeling the mission had been disorganized. Pilot Conrad Gus Shin, who flew R-4D aircraft from the carrier USS Philippine Sea during the operation, said afterward that the team did not really know what they were doing. They did not know about precision flying standards or what exactly they were looking at when they flew over the terrain. Senior Navy officials called the operation a success. The men who executed it described confusion about their roles and objectives. Both things can be true at the same time. The operation ended in late February 1947, just 3 months after the ships left port. The official reason was the early approach of Antarctic winter and deteriorating weather conditions. Critics within the task force felt the abrupt ending reflected the mission's lack of clear organization more than the weather. The fleet withdrew to the United States. Byrd and Admiral Nimitz were filmed together in a ceremony documented by military photographers as the USS Mount Olympus made its way back up the Potomac and Anacostia rivers. The documentary film, shot by military photographers during the operation, was released in theaters under the title The Secret Land. It was narrated by actors Robert Taylor, Robert Montgomery, and Van Heflin, all 3 of whom had served in the Navy during World War II. It won the Academy Award for Best Documentary Feature in 1948, The footage is publicly available in the National Archives. The operation is documented in a 543-page official Navy report. None of it is hidden. Now, the conspiracy version of Operation High Jump. The versions that circulate online, on YouTube, TikTok, and the corners of the internet devoted to suppressed truths, claim that the real purpose of the mission was to destroy secret Nazi bases built in Antarctica during World War II, or to make contact with extraterrestrial beings, or to find an entrance to a hollow Earth. Admiral Byrd is frequently quoted as having described encounters with a warm land beyond the South Pole and contact with advanced non-human beings. Those quotes come from a fabricated diary, a document with no verified chain of custody, no archival source, and no connection to any authenticated Byrd writing. The real Byrd diaries and official correspondence are held in the National Archives and the Byrd Polar Research Center archives at Ohio State University. They describe polar operations, not underground civilizations. The Nazi Antarctic base theory. The idea that Germany built a secret installation called New Swabia, or Base 211, has been investigated repeatedly by historians of the Third Reich and found to have no documentary basis. Germany did conduct Antarctic expeditions in 1938 and 1939, dropping territorial marker buoys from aircraft and mapping a section of the continent they named Neuschwabenland. That is documented. There is no evidence of a wartime base, no German military records referencing one, no physical trace of a structure, and no credible source. The theory was invented and circulated in post-war Germany, adopted by neo-Nazi mythmakers, and eventually found its way into online content mills. What Operation High Jump actually represents is something more historically interesting than aliens or Nazis. It was the United States government using the machinery of science, research stations, geological surveys, atmospheric data, photographic mapping, as a vehicle for strategic territorial positioning at the start of the Cold War. The science was real. The secrecy was about land claims and Cold War competition, not suppressed discoveries. And when the treaty eventually made those land claims legally frozen and impossible to act on, the United States had already established the footprint it needed to remain a dominant presence on the continent. The operation also set the logistical template for everything that came after. The lessons from High Jump about icebreaker requirements, helicopter reconnaissance, airstrip construction on ice, cold weather equipment limitations, and the impossibility of sustained Antarctic operations without proper support infrastructure fed directly into Operation Deep Freeze, which began in 1955 and still operates today as the U.S. military's logistical support program for American Antarctic science. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. What nobody on those 13 ships could have known in 1947 was what was directly beneath their feet as they sailed through the pack ice. Kilometers below the ice sheet above which they flew their mapping aircraft, something existed that their radar equipment could not yet see and their instruments could not yet measure. It would take another half-century of satellite technology, ice-penetrating radar, and gravitational mapping to begin to understand what the Antarctic ice sheet was sitting on top of, and what was moving underneath it. Section 3. The 231 Hidden Lakes. An entire subglacial ocean beneath the ice. The Antarctic ice sheet is not sitting on flat, dry rock. Underneath it, spread across the entire continent, is a world that most people have never heard of. A hidden network of lakes, rivers, and drainage systems sealed under kilometers of ice, completely dark, under enormous pressure, and very much alive. Scientists have known pieces of this for decades, but what they confirmed in 2025 fundamentally changed the picture of what is down there. Start with the basics of how these lakes exist at all. The Antarctic ice sheet is not a static block. It is constantly moving, grinding slowly across the bedrock underneath it. That grinding generates friction, and friction generates heat. At the same time, the Earth's interior is not cold. Geothermal heat rises continuously from the planet's core through the mantle and into the crust. When that heat reaches the base of the ice sheet, it can melt the very bottom of the ice, without the surface showing any sign of it whatsoever. The result is liquid water, trapped between the underside of the ice above and the bedrock below, under pressures that would crush most things, in total darkness, with no connection to the surface world above. Those pockets of water are subglacial lakes. They have been forming and existing under Antarctica for an extraordinarily long time. In some cases, millions of years. The largest of them is Lake Vostok, located in East Antarctica beneath Russia's Vostok Research Station. Lake Vostok is roughly the size of Lake Ontario, one of the 5 Great Lakes of North America. and sits under approximately 4 kilometers of ice. It holds an estimated 5,000 to 65,000 cubic kilometers of water. It is one of the largest lakes on Earth by volume, and it has been completely sealed from the surface for what researchers estimate is somewhere between 15 and 25 million years. For context, that is before modern humans existed, before most current species existed. The water in Lake Vostok has been sitting there, isolated and pressurized, since the continent it sits under was still transitioning into the frozen state we know today. For most of the 20th century, scientists knew only a handful of these lakes existed. Lake Vostok was identified through airborne radar surveys in the 1970s. By the time serious subglacial mapping began in earnest, researchers had cataloged around 150 lakes in total. Then, satellite technology changed everything. The European Space Agency's Cryosat-2 satellite was launched in 2010 with a specific mission: to measure changes in the thickness of polar ice sheets and sea ice around the world. It carries a radar altimeter, an instrument that bounces radar signals off the surface of the ice and measures how high that surface sits, with precision down to a few centimeters. The reason that matters for subglacial lakes is subtle but important. When a lake beneath the ice fills up with water, the pressure pushes the ice sheet above it slightly upward. When the lake drains, the ice above sinks back down. The changes are measured in meters, not centimeters, large enough for Cryosat-2 to detect clearly from orbit. A research team led by Sally Wilson, a doctoral researcher at the University of Leeds in the United Kingdom, spent years analyzing a full decade of Cryosat-2 data from 2010 to 2020, looking specifically for those rise and fall signatures across Antarctica's margins. What they found was published in Nature Communications on September 19, 2025. They identified 85 previously unknown active subglacial lakes. Before that paper was published, the known count of active subglacial lakes in Antarctica stood at 146. Active means the lake is doing something: filling, draining, changing. The 85 new discoveries brought that total to 231, an increase of 58% in a single study. The total number of all subglacial lakes in Antarctica, active and stable combined, now exceeds 400. Wilson explained the core challenge of this kind of research plainly. These lakes are buried under hundreds of meters of ice. Observing them fill and drain is incredibly difficult because the cycles take months or years to complete. Before the 2025 study, only 36 complete fill and drain cycles had ever been documented anywhere in the world. The Leeds team observed 12 more complete cycles in their data alone, bringing the global total to 48. 50 of the 85 newly identified lakes showed both filling and draining behavior in the dataset, meaning they cycled through at least one direction of change during the 10-year observation window. 6 of the newly discovered lakes sit within 8 kilometers of the grounding zone, the line where the Antarctic ice sheet lifts off the bedrock and begins to float on the ocean. That proximity matters enormously for understanding the relationship between subglacial hydrology and sea level rise, which is explained below. The research also identified 5 interconnected subglacial lake networks, systems where multiple lakes are hydraulically connected to each other underground. The team observed what they called concurrent upstream drainage and downstream filling events, a lake higher up in the system draining at roughly the same time a lower lake filled up. That is not coincidence. That is a plumbing system. Water is flowing from one lake to another through channels carved in or between the bedrock and the base of the ice. Anna Hogg, a professor of Earth observation at the University of Leeds and a co-author on the study, described the subglacial hydrology of Antarctica as far more dynamic than previously thought. The picture that had existed before, of mostly static, isolated pockets of water, was wrong. There are also 25 identified clusters of lakes, meaning groups of lakes sitting close together in what appear to be related geological settings. The combination of interconnected networks and proximity clusters suggests something closer to a drainage basin system than a collection of isolated ponds. Now, the question of why any of this matters beyond scientific curiosity. When a subglacial lake drains, when it releases its stored water outward along the base of the ice sheet, that water acts as a lubricant. Ice grinding against dry rock moves slowly. Ice sliding over a thin film of water moves much faster. This is not theoretical. Researchers have directly observed glaciers accelerating their flow toward the ocean during and after subglacial drainage events. More ice flowing faster into the ocean means more ice entering the sea, melting, and contributing to global sea level rise. The 85 new lakes identified in the 2025 study, particularly the 6 sitting close to the grounding zone, represent 85 more potential lubricant sources for the glaciers sitting above them. The 2025 study noted explicitly that the numerical models currently used to project how much Antarctica will contribute to sea level rise do not include subglacial hydrology. The models assume the ice sheet base behaves in certain ways that the actual data does not support. Incorporating the new lake location data, their drainage cycle timelines, and the interconnected network maps into those models is now a research priority, because the projections could change significantly once it is done. Drilling into these lakes is the only way to know what is actually in them, and doing it without contaminating a system that has been sealed for millions of years is one of the hardest technical challenges in polar science. The first successful contamination-free access to a subglacial lake happened in 2013, when an American research team drilled into Whillans Subglacial Lake in West Antarctica. What they found when they pulled their samples up surprised almost everyone involved. The water was teeming with microbial life, not traces of life, not ambiguous chemical signatures, actual living organisms, actively metabolizing, actively reproducing, in water that had been sealed from sunlight and the surface atmosphere for thousands of years. The microbial community was dominated by round-shaped cells, alongside rod-shaped bacteria, spirochetes, and filamentous organisms. Many of them were cycling nitrogen, processing ammonium and nitrite as energy sources in complete darkness. The community showed signs of adaptation to fluctuating conditions, which means it was not just barely surviving. It had evolved specific strategies to thrive in that environment. The second successful contamination-free access happened in 2025. The Korea Polar Research Institute, working with American research teams as part of the Subglacial Antarctic Lake Scientific Access Project, drilled through 1,085 meters of ice to reach Mercer Subglacial Lake. Their findings, published in Nature Communications in August 2025, revealed microbial communities that were genetically distinct from anything found in marine or surface environments. The organisms were not variants of known species. They were organisms that had been isolated so completely for so long that they had diverged into entirely new biological territory. The researchers analyzed 374 single-cell amplified genomes and found that most belonged to previously undescribed species. These 2 successful drilling operations represent the only times in human history that scientists have accessed a subglacial lake without contaminating it. Both happened in West Antarctica. The United States research teams involved remain the only groups to have successfully completed the feat. Hundreds of other subglacial lakes have never been touched. The astrobiological implications are significant enough that NASA and the European Space Agency both pay attention to Antarctic subglacial lake research. Jupiter's moon Europa has a global ocean of liquid water sealed under a shell of ice, estimated to be between 10 and 30 kilometers thick. Saturn's moon Enceladus has a subsurface ocean that actively vents water vapor through cracks in its ice shell. If life can exist in Mercer Subglacial Lake and Whillans Subglacial Lake, drawing energy from chemistry rather than sunlight, surviving without any connection to the surface world, then the argument that oceans on other planets must be sterile because they are sealed under ice becomes much harder to make. The January 2026 bedrock mapping study added another layer to this picture. Published in the journal Science, the research used a technique called ice flow perturbation analysis to produce an X-ray of the continent's interior. It identified a hidden trench in the Maud subglacial basin, stretching nearly 400 kilometers, the length of the drive from London to Newcastle, carved into the bedrock before the ice sheet formed. The Gamburtsev subglacial mountains in central East Antarctica turned out to be a full alpine range with peaks, ridges, and carved valleys, buried entirely under the highest point of the ice sheet, comparable in scale to the Appalachians. These geological structures, the mountains, the trenches, the basins, are the physical containers that determine where subglacial lakes form, how they connect, and where the water goes when they drain. What the 2025 and 2026 research collectively established is that Antarctica is not a simple block of frozen water sitting on flat ground. It is a geologically complex continent with its own internal weather system, lakes filling and draining on timescales of months and years, rivers running in total darkness, mountains guiding the flow of ice above them toward or away from the sea. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. But the subglacial lake system is not the only thing moving beneath the Antarctic ice. Scattered across the continent's bedrock, hidden under the same kilometers of ice that conceal the lakes, are structures that generate their own heat from an entirely different source. And whether they are currently active or dormant may be one of the most consequential unanswered questions in Antarctic science. Section 4. The 138 volcanoes no one knew were there. Antarctica has a volcano problem. Not in the sense that the continent is about to erupt, in the sense that for most of modern science, nobody knew how many volcanoes were under the ice. And when researchers finally looked properly, what they found was far larger than anyone expected. The number that emerged from the most comprehensive survey ever done of the West Antarctic ice sheet's volcanic geology was 138. And the part that matters most is not the total. It is how many of those 138 nobody knew existed. Start with what was visible before the 2017 survey. Some Antarctic volcanoes are obvious. Their peaks break through the surface of the ice sheet, rising above the white landscape as rocky summits that geologists could identify, sample, and study. Before 2017, researchers had documented 47 such structures in West Antarctica, volcanic cones whose tops were exposed enough to confirm what they were. That was the baseline. 47 known volcanoes in the West Antarctic ice sheet region. The 2017 survey changed that number dramatically. A research team assembled data from ice-penetrating radar surveys, satellite imagery, and gravitational field measurements, tools that can see through the ice to the rock beneath, and systematically examined the West Antarctic ice sheet for volcanic signatures. They were looking for cone-shaped features in the bedrock, cross-referenced against supporting geological data that would confirm a volcanic origin rather than just an irregular rock formation. They initially flagged 180 candidate structures. After rigorous filtering, removing the 50 that did not have sufficient supporting evidence, they confirmed 138 volcanic cones in total. That means 91 of those 138 volcanoes had been sitting completely hidden under the ice, unknown to science, until radar and satellite technology developed enough to find them. These are not small features. Volcanic cones by their nature are substantial geological structures. The 91 hidden ones were simply buried deep enough under the ice that no surface expression existed to hint at what was below. The concentration of these volcanoes in certain areas of West Antarctica is significant. Marie Birdland, the region of the continent that includes the locations of the Thwaites and Pine Island glaciers, turns out to be one of the more volcanically dense regions on Earth. Researchers calculated approximately one volcano per every 11,200 square kilometers of area in that zone. For comparison, the East African Rift, one of the most volcanically active regions on the planet, responsible for the chain of volcanoes running through Ethiopia, Kenya, Tanzania, and into Mozambique, has roughly one volcano per 7,200 square kilometers. Antarctica's own central rift system has one per 7,800 square kilometers. Marie Birdland is not quite as dense as those regions, but it is not far behind, and it sits under one of the most unstable and rapidly changing portions of the ice sheet on Earth. 29 of West Antarctica's confirmed volcanoes have heights exceeding 1 kilometer above the surrounding bedrock. Many of these are in Marie Birdland and the central rift system. They are entirely covered by ice, their summits never breaking the surface, their existence, until recently, entirely theoretical. Whether any of these hidden volcanoes are currently active is the question that matters most, and that science cannot yet fully answer. To be precise about what active means in this context, a volcano can be classified as active if it has erupted in the last 10,000 years, the period geologists use as their standard threshold. It can be classified as dormant if it has not erupted in that time frame, but is not considered permanently extinct. And it can be classified as extinct if there is no reasonable geological expectation of future activity. The problem with the 91 hidden volcanoes is that without direct sampling of the rock and the heat profile beneath the ice, classifying them definitively is not possible. Scientists are working on deploying instruments capable of detecting geothermal heat signatures beneath the ice, but that work is ongoing. What can be said with confidence is this: if any of these hidden volcanoes are active, or even dormant but warm, the heat they generate affects the ice sheet above them from below. That heat adds to the geothermal warmth already melting the base of the ice, contributing to subglacial lake formation and the lubricating water films that accelerate glacial movement. In an ice sheet already losing mass from warming ocean water attacking it from the sides, additional heat from below is not a minor variable. There is also a more unsettling long-term dynamic at work here, involving a process called isostatic rebound. The Antarctic ice sheet is extremely heavy. It has been sitting on the continent's bedrock for millions of years, and its weight compresses and depresses the crust beneath it. In some parts of Antarctica, the bedrock sits more than 2.5 kilometers below sea level, pushed down by the weight of the ice on top of it. This matters for volcanoes because the pressure exerted by the overlying ice acts as a suppressive force on the volcanic systems below. Heavy ice sitting on top of a volcanic system keeps the pressure on the magma from building up enough to drive an eruption. Remove that ice, and the pressure balance changes. As Antarctica loses ice mass due to climate change, that suppressive weight decreases. The crust, relieved of pressure, begins slowly to rebound upward, a process that has been documented in Greenland, where glacial retreat has been underway longer and the rebound is measurable. In Antarctica, where the ice sheet is far larger and the potential rebound displacement far greater, the effect on volcanic systems buried beneath it could be significant. Researchers studying this process note that the risk of volcanic eruptions in West Antarctica increases as ice mass decreases, as the isostatic pressure that has been keeping those volcanic systems in check gradually lifts. This is not a prediction that Antarctica is about to experience a chain of volcanic eruptions. It is a description of a physical relationship between ice load and volcanic pressure that has geological precedent and that climate models incorporating ice loss trajectories need to account for. The one Antarctic volcano that needs no speculation about whether it is active is Mount Erebus. Mount Erebus sits on Ross Island, off the coast of East Antarctica, and stands 3,794 meters tall. It is the most active volcano on the continent, and one of a very small number of volcanoes in the world that maintains a persistent lava lake, a pool of molten rock that sits open at the summit, visible to aircraft and researchers at the nearby scientific stations. The New Zealand Scott Base and the American McMurdo Station are both located on Ross Island, making Erebus one of the most closely observed active volcanoes on Earth by default. Scientists based there can see it from their stations. Erebus erupts regularly in what volcanologists call strombolian eruptions, relatively small explosions that hurl chunks of lava called bombs out of the crater. These are not cataclysmic events. They are the normal behavior of a volcano with an open vent lava lake venting pressure on a routine basis. The lava lake itself has been observed continuously since at least 1972, making it one of the longest documented persistent lava lakes on the planet. The chemistry of the gases Erebus releases, measured by instruments deployed around the crater, provides data about what is happening in the volcanic system below and serves as a reference point for understanding volcanic behavior in polar environments. Erebus is the visible face of Antarctic volcanism. The 138 cones buried under the West Antarctic ice sheet are the invisible face, and the invisible face is the one that carries the greater scientific uncertainty. What makes the volcanic picture genuinely complicated is the way it intersects with everything else happening under the ice simultaneously. The subglacial lakes discussed in Section 3 exist because of geothermal and frictional heat melting the ice base. Volcanic systems beneath the ice contribute additional heat to that same base. The subglacial rivers and drainage networks that move water from lake to lake also move geothermally heated water. The rock chemistry of volcanic terrain, rich in sulfur compounds and other minerals, influences the chemistry of the water that moves through it, which in turn influences what kinds of organisms can survive in the lakes that water flows into. The West Antarctic ice sheet is essentially sitting on top of one of the more geologically active regions of the planet, with a volcanic field beneath it whose full character is still being mapped and whose current activity levels are still being determined. The 2017 survey that found the 91 hidden volcanoes was the first comprehensive attempt to count them. It will not be the last, and the number may change again as techniques improve. There is also a feedback relationship between volcanic heat and ice loss that researchers are only beginning to quantify. Ice loss reduces pressure, which may increase volcanic activity, which generates more heat, which accelerates ice loss from below, which reduces pressure further. Whether this loop is significant enough to be a meaningful driver of ice sheet behavior on human timescales, decades rather than centuries, is an active area of research without a settled answer. What can be said with certainty is that the bedrock under Antarctica is not inert. It is geologically active, thermally variable, and in ways that matter directly for the behavior of the ice sheet sitting on top of it. The continent that looks from the surface like a featureless expanse of white is, from below, a landscape of hidden mountains, lakes, rivers, and volcanoes interacting in ways that took until the 21st century to begin to see clearly. The heat from below, the water in motion underground, and the volcanic structures contributing to both, all of it flows, ultimately, toward the edges of the continent. And at those edges, some of the ice the system is moving has been identified by scientists as the single most consequential piece of frozen water on Earth for the future of every coastal city in the world. Section 5. The Thwaites Doomsday Glacier. Real-time collapse data. There is a glacier in West Antarctica that a significant number of climate scientists describe as the most important and most dangerous piece of ice on Earth. It sits in a remote part of the continent, far from any research station, difficult and expensive to reach, and for most of the 20th century, almost completely unstudied. Its name is Thwaites. The nickname that journalists started using, the Doomsday Glacier, is considered melodramatic by some researchers. But when you go through the actual findings of the people who have spent years drilling into it, sailing under it, and mapping its retreat with satellites, the nickname does not feel entirely unreasonable. Thwaites is enormous. It covers roughly the same area as the state of Florida, about 192,000 square kilometers of ice. It flows from the interior of West Antarctica toward the Amundsen Sea, where it meets the ocean at a floating edge called an ice shelf. The glacier is not a fixed object. It is in constant motion, flowing toward the sea under the force of gravity, adding ice to the ocean at its edges, while being replenished by snowfall inland. The question that drives all Thwaites research is whether the rate at which it is adding ice to the ocean is accelerating beyond the point of recovery. The numbers behind that question are worth stating plainly. Thwaites currently loses approximately 50 billion tons of ice per year to the ocean. That makes it single-handedly responsible for about 4% of total global sea level rise right now. If it melted completely, every cubic meter of ice in the glacier converted to water and added to the ocean, global sea levels would rise by approximately 65 centimeters, or a little over 2 feet. That figure alone would be catastrophic for low-lying coastal regions and island nations. But the 65 centimeters is not the number that keeps researchers awake at night. Thwaites functions as a structural barrier. It sits at the marine-facing edge of the West Antarctic ice sheet, a massive basin of ice that covers most of West Antarctica and sits in a bowl of rock that in many places lies well below sea level. Thwaites and the neighboring Pine Island Glacier are the primary glaciers holding back the rest of that basin from flowing into the Amundsen Sea. If Thwaites retreats far enough and loses enough structural integrity, the warmer ocean water it has been blocking gains access to the ice sheet behind it. The ice sheet behind it is far larger than Thwaites itself. Scientists estimate that if Thwaites and the ice it currently supports were to ultimately collapse, global sea levels could rise by more than 3 meters. In some projections, considerably more. That is the scale of what is at stake. Understanding why Thwaites is particularly vulnerable requires understanding the shape of the ground it sits on. The bedrock beneath Thwaites slopes downward as you move inland from the coast. This is the exact opposite of the geography you would want for a stable glacier. As Thwaites retreats from its current position, it exposes new sections of its base to the ocean, sections that are lower than the previous ones, meaning deeper ocean water, meaning warmer water, meaning faster melting. This self-reinforcing process, where retreat exposes deeper ice which melts faster, which causes more retreat, is called marine ice sheet instability. Scientists first identified this theoretical vulnerability in Thwaites and Pine Island Glacier back in the 1970s and 1980s, which is when researchers began describing West Antarctica's Amundsen Sea sector as the weak underbelly of the ice sheet. Those early theoretical concerns have been confirmed by decades of subsequent observation. In 2018, the United States and United Kingdom jointly funded the International Thwaites Glacier Collaboration, a research program bringing together roughly 100 scientists to study the glacier directly. The funding commitment was significant, a dedicated, multi-year, multi-institution effort to answer the questions that satellite observation alone could not resolve. The collaboration ran 6 years of fieldwork, deploying ice-breaking ships, drilling equipment, autonomous underwater vehicles, and remote sensing instruments at one of the most remote and inaccessible locations on Earth. In May 2024, a team led by researchers at the University of California, Irvine and the University of Waterloo published findings in the Proceedings of the National Academy of Sciences that changed how scientists understand the mechanism of Thwaites melting. Using high-resolution satellite radar data, they found direct evidence that warm, high-pressure seawater is intruding kilometers beneath the grounded portion of the glacier, the section of the ice that still rests on bedrock rather than floating on the ocean. This was the first satellite-based evidence of ocean water pushing that far inland under the ice. Christine Dow, professor at the University of Waterloo and a co-author on the study, described Thwaites as the most unstable place in Antarctica and said the worry is that the speed of change is being underestimated, with potentially devastating consequences for coastal communities worldwide. The same 2024 research established that instead of a narrow grounding line separating the glacier's grounded and floating portions, there is actually a wider grounding zone of 2 to 6 kilometers that is regularly exposed to ocean water. During strong spring tides, meltwater penetrates a further 6 kilometers inland beyond that zone. The practical implication is that the ocean is eating at the glacier from below across a much larger area than previous models assumed. Existing projections of how fast Thwaites will retreat may need to be revised upward. In August 2024, the ITGC deployed an autonomous underwater vehicle called RAN, a 7-meter bright orange robotic submarine, beneath 350 meters of Thwaites ice, producing the first detailed maps ever made of the underside of the glacier. Those maps confirmed the complexity of the melt patterns occurring below the ice shelf and provided data that researchers had previously only been able to estimate from surface measurements. RAN subsequently went missing in February 2024 during another deployment, a loss the collaboration publicly acknowledged, describing the vehicle as a highly valued component of their research program. The ITGC published its consolidated findings in September 2024, representing the conclusions of 6 years of research. Rob Larder, a marine geophysicist at the British Antarctic Survey and co-lead of the project, stated that retreat has accelerated considerably over the past 30 years. Eric Rigno, a glaciologist at the University of California, Irvine, and a senior member of the collaboration, said directly that he remains very worried that this sector of Antarctica is already in a state of collapse. The collaboration's overall assessment used the word grim. However, the September 2024 findings also contained a more cautious note on one of the most alarming specific scenarios that had been discussed. A study published in Science Advances, produced by researchers at Dartmouth College and the University of Edinburgh, examined a process called marine ice cliff instability. The idea that as the ice shelf at the edge of Thwaites sheds icebergs, the cliff face left behind would grow too tall to support itself and begin collapsing under its own weight, triggering a runaway chain reaction. The updated high-resolution models found that this particular mechanism is unlikely to occur during the current century. The glacier's tendency to flow faster when released from grounding constraints keeps the ice cliff from reaching the height threshold that would trigger catastrophic collapse. Professor Matthew Morleghem of Dartmouth, the study's lead author, was careful to note that this does not mean Antarctica is safe, only that the most extreme projections for the 21st century are now considered less probable. What remains firmly in the projections is steady, accelerating retreat that could add up to 6 centimeters of sea level rise from Thwaites alone by the end of this century. That contribution is set to occur regardless of future emissions decisions, because the warming already in the system from past emissions is sufficient to drive it. Under the worst-case emission scenario, models published in Earth's Future project that Thwaites and the ice sheets it currently supports could collapse by the year 2300, adding more than 4 meters to global sea levels. In December 2025, a study published in the Journal of Geophysical Research documented 20 years of accelerating fracture development on the Thwaites eastern ice shelf, the floating portion of the glacier that extends over the ocean. The research, led by Debangshu Banerjee from the Center for Earth Observation Science at the University of Manitoba, used satellite and GPS data to map how fractures around a major shear zone have multiplied and widened over 2 decades, as the shelf gradually loses its grip on a stabilizing underwater pinning point at its northern edge. The pattern of fracture development described in that paper is consistent with a shelf in the early stages of structural disintegration, a process that, once it passes certain thresholds, cannot be reversed by any current technology. What the combined body of ITGC research produced is not a prediction of imminent catastrophe. It is something more precise, and in some ways more unsettling. A detailed description of a glacier already in an irreversible process of retreat, moving at an accelerating pace, driven by mechanisms that existing climate models underestimated and carrying consequences that will play out over this century and the next, regardless of decisions made about emissions today. The people who know Thwaites best, the scientists who have spent years on the ice, in the water beneath it, and analyzing its data, consistently use language that reflects genuine scientific concern rather than catastrophism. Rignow's statement about already being in a state of collapse is not the language of a researcher seeking attention. It is the language of a person who has spent decades studying a specific system and has reached a conclusion about its direction that the data no longer allows him to avoid. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. The volcanoes under the ice and the subglacial lakes add heat and water to the system from below. The warming ocean adds heat from the sides and the bottom edge. The fractures developing on the eastern ice shelf add structural vulnerability from within. These forces do not operate in isolation from each other. And the device that has given scientists the clearest real-time picture of all of them, the tool that sees through the ice, tracks the movement of hidden water, and detects the earliest signatures of change from hundreds of kilometers above, was built not on a ship or on the ice surface, but deep within the ice itself, at the most remote point on the continent. Section 6. The IceCube Neutrino Observatory, the strangest building on Earth. At the geographic South Pole, buried under more than a kilometer of Antarctic ice, there is a structure that has no equivalent anywhere else on Earth. It has no walls, no roof, and no floor in any conventional sense. It cannot be visited in person by anyone without serious polar expedition support. It has been operating continuously since 2010, staffed year-round by 2 people who spend the Antarctic winter, the darkest, coldest months on the planet, living at the Amundsen-Scott South Pole Station, directly above it. It is called IceCube, and what it is designed to detect is so small, so fast, and so elusive that the only material on Earth capable of catching it in meaningful numbers is a full cubic kilometer of ancient Antarctic ice. IceCube is a neutrino observatory. To understand what that means and why Antarctica was the only place it could be built, you need to understand what a neutrino is. A neutrino is a subatomic particle with almost no mass and no electric charge. It was first theorized in 1930 and first detected experimentally in 1956. Neutrinos are produced in enormous quantities by nuclear reactions. The sun produces them in vast numbers. The Earth's atmosphere produces them when cosmic rays hit it, and the most violent events in the universe produce them at energies that dwarf anything achievable in a laboratory. Billions of neutrinos pass through every square centimeter of your body every second. Every second, without stopping, without you feeling anything, without interacting with any part of you in any detectable way. They pass through the Earth as though it is not there. They pass through lead, concrete, and steel with almost complete indifference. Almost nothing stops a neutrino. That property is exactly what makes them scientifically valuable and practically impossible to study. Because they interact with almost nothing, they travel in a straight line from wherever they were created to wherever they end up, undeflected by magnetic fields and unabsorbed by the matter they pass through. A high-energy neutrino arriving at Earth carries a direct pointer back to whatever created it: a supernova, a colliding neutron star, a galaxy with a supermassive black hole consuming matter at its center. No other particle provides that kind of unobstructed, directional information across cosmic distances. But to catch even a tiny fraction of the neutrinos passing through the Earth requires an enormous detector and an extraordinarily transparent medium for the rare interactions to occur in. The solution developed by physicist Francis Halzen at the University of Wisconsin-Madison, building on an idea originally proposed in 1960 by Soviet physicist Moisey Markov, was to use the ice itself. When a neutrino does interact, rarely but occasionally, it produces a secondary charged particle moving faster than light travels through ice. Light does not travel at the same speed in ice as it does in a vacuum. The speed of light in a vacuum is the universal maximum, but light moving through a medium like water or ice travels slower. A charged particle produced by a neutrino interaction can exceed that reduced speed, and when it does, it creates a cone of blue light called Cherenkov radiation, the optical equivalent of a sonic boom. That flash of blue light lasts only a fraction of a second and is extraordinarily faint. Detecting it requires sensors embedded in ice that is exceptionally clear. No bubbles, no impurities, no internal scattering that would obscure the signal. The deep Antarctic ice at the South Pole, formed over hundreds of thousands of years of compacted snowfall, is the clearest natural ice on Earth. Below approximately 1,400 meters, the pressure has eliminated essentially all air bubbles from the ice, leaving a medium so optically clear that the blue flashes from neutrino interactions can be detected by sensors tens of meters away from where the interaction occurred. No other location on Earth offers a comparable volume of that quality of natural ice. Construction of IceCube began at the South Pole in 2004. The building method was unlike anything previously attempted in polar science. Teams working during the Antarctic summer, November through February, used a hot water drill to melt holes 60 centimeters in diameter straight down into the ice, reaching depths of up to 2,450 meters. That is deeper than the deepest point of the Grand Canyon from rim to bottom. Each hole took approximately 40 hours to drill. Once a hole reached its target depth, a string of 60 digital optical modules was lowered into it before the water refroze. Each module is a glass sphere 33 centimeters in diameter, containing a photomultiplier tube, a device sensitive enough to detect a single photon of light, along with the electronics to record and timestamp whatever it detects. The process was repeated 86 times over 7 Antarctic summer seasons, from 2004 through 2010. On December 18, 2010, just after 6 in the evening New Zealand time, the last of the 86 strings was lowered into the ice. IceCube was complete. The finished detector contains 5,160 digital optical modules arranged across 86 strings, spanning a volume of 1 full cubic kilometer. The sensors sit between 1,450 and 2,450 meters below the surface. At the center of the array, 8 strings were deployed in a denser configuration, with modules spaced 7 meters apart vertically, rather than the standard 17 meters, forming an inner subdetector called Deep Core that extends IceCube's sensitivity to lower energy neutrinos. At the surface directly above the array sits IceTop, a set of 81 stations, each containing 2 ice-filled tanks equipped with optical sensors designed to detect cosmic ray air showers hitting the atmosphere. The total investment in construction was funded by the U.S. National Science Foundation as a major research equipment and facilities construction grant, with additional contributions from funding agencies in Belgium, Germany, and several other countries. The University of Wisconsin-Madison is the lead institution. The IceCube collaboration now includes more than 350 scientists at 58 institutions across 14 countries. On May 13, 2011, IceCube took its first complete physics run as a fully configured facility. What followed over the next decade was a sequence of discoveries that reshaped particle astrophysics. In 2012, IceCube detected the 2 highest energy neutrinos ever observed at that point in history. The particles, with estimated energies of approximately 1 quadrillion electron volts, a unit written as 1 peta-electron volt, were nicknamed Bert and Ernie by the team. Shortly after those 2 detections, IceCube observed 26 more very high-energy events, establishing that a population of extremely energetic neutrinos was arriving from outside the solar system. This was the first direct detection of neutrinos of cosmic origin, particles produced not in the Sun or the Earth's atmosphere, but somewhere far out in the universe. In 2015, IceCube published a refined analysis confirming the cosmic origin of these high-energy neutrinos and producing the most accurate measurements to date of their energy spectrum and composition. The source or sources responsible remained unknown. The energies were confirmed as extragalactic, but pointing back to a specific object required catching a neutrino from a known direction at a moment when other telescopes could confirm something was happening there. That breakthrough came in September 2017. IceCube detected a single high-energy neutrino, designated IceCube 170922A, and its directional reconstruction pointed back to a specific location in the sky. An alert was sent to observatories around the world. Within days, multiple telescopes, including the Fermi Gamma Ray Space Telescope and the MAGIC Telescope in the Canary Islands, confirmed that a known object at those coordinates was in a state of elevated activity. The object was a blazar designated TXS 0506 plus 056, a galaxy approximately 3.7 billion light-years from Earth, with a supermassive rotating black hole at its center, pointing one of its high-energy jets directly toward the Milky Way. The neutrino had traveled 3.7 billion years from that black hole's jet to the Antarctic ice. This was the first time in history that a high-energy neutrino had been matched to a specific astronomical source. The result was published in Science and marked the beginning of what researchers call multi-messenger astrophysics, coordinating neutrino detections with light, radio waves, and gravitational wave observations to build a complete picture of violent cosmic events. In 2021, IceCube confirmed the detection of a Glashow resonance event. This is a specific interaction predicted in 1960 by physicist Sheldon Glashow, later a Nobel laureate, in which an antineutrino interacts with an electron to produce a W boson particle at a precise energy of 6.3 peta-electron volts. No particle accelerator currently built can reach that energy. IceCube detected it in the Antarctic ice. The confirmation was published in Nature and represented the verification of a theoretical prediction that had waited 61 years for experimental confirmation. In June 2023, IceCube published results in the journal Science, announcing the detection of the first high-energy neutrinos confirmed to originate from within the Milky Way galaxy itself. Previous detections had been of extragalactic neutrinos, particles arriving from distant galaxies. The 2023 result identified a diffuse glow of neutrino emission coming from the plane of our own galaxy, produced by cosmic ray interactions with the gas and dust distributed throughout the Milky Way. The result was produced using a machine learning analysis of 10 years of IceCube data and required distinguishing a faint galactic signal from the much larger background of atmospheric and extragalactic neutrinos the detector records continuously. IceCube records approximately 2,600 events per second. Most of those are atmospheric neutrinos, produced when cosmic rays hit the upper atmosphere. Out of the roughly 100,000 neutrinos detected each year, only a few hundred are from galactic or extragalactic sources. Identifying those few hundred from within the millions of atmospheric events requires sophisticated filtering algorithms running on a computing cluster maintained at the University of Wisconsin-Madison. In February 2026, construction began on the IceCube upgrade, the first major expansion of the detector since its completion in 2010. The upgrade will add more than 700 new and enhanced optical modules to the ICE, deployed in the deep core region at the center of the array. The new modules use improved sensor technology and multi-directional light collection to extend IceCube sensitivity to lower energy neutrinos and improve the resolution of all data, past and future, collected by the existing detector. The upgrade also serves as the engineering prototype for IceCube Gen 2, a planned next-generation detector that would instrument a volume of ice approximately 8 times larger than the current array. The 2 staff members who winter over at the South Pole each year, the people who keep IceCube running through the 4 months of Antarctic winter when the station is cut off from resupply and the temperature drops below -60 degrees Celsius, maintain the detector systems, respond to alerts, and have unobstructed views of the Milky Way and the southern aurora during the long polar night. They are, for those months, the only people on Earth within 2 kilometers of a detector that is simultaneously watching the entire universe for the most energetic particles nature produces. IceCube is fully documented, publicly funded, and operated by an international collaboration whose membership and research output are published continuously. Its existence is not a secret. Its findings are published in the most prominent scientific journals in the world. What makes it extraordinary is not concealment. It is the sheer audacity of the engineering and what that engineering has revealed about the most violent processes in the universe. But as remarkable as IceCube is, it is looking outward at the cosmos above. What it is embedded in tells a different story. The ice around its sensors is not just a detector medium. It is a physical archive, layer by layer, of every year of Earth's atmospheric history, stretching back further than any other record that exists. And what is preserved in those layers has already rewritten what scientists believed about the climate of the planet long before any human civilization existed. Section 7. The Hidden Continent Beneath the Ice. The January 2026 Bedrock Map. Antarctica looks simple from the outside. From a satellite photograph or a globe, it is a white oval sitting at the bottom of the world, featureless and uniform. That appearance is completely misleading. Underneath the ice sheet covering it, Antarctica has mountains, valleys, plains, deep trenches, ancient riverbeds, and geological structures that rival anything visible on the surface of any other continent. For most of scientific history, that hidden world was almost entirely unknown, not because no one was trying to map it, but because the tools did not exist to do it properly. In January 2026, that changed. To understand what the January 2026 study actually achieved, you first need to understand how difficult Antarctic bedrock mapping had been for the previous century. The ice sheet sitting on top of Antarctica is not thin. In many places, it is between 2 and 4 kilometers thick. The average thickness across the entire continent is approximately 2.16 kilometers. That is more than 2 kilometers of compressed ice sitting between any instrument on the surface and the rock underneath. For decades, the primary tool for seeing through that ice was airborne radar. Aircraft equipped with specialized radar systems that send pulses downward through the ice and measure the return signal bouncing off the bedrock below. The time it takes for the pulse to return tells you how far down the rock is. Fly a grid pattern over a large area and you can build a map of the bedrock depth. The problem with that approach is coverage. Antarctica is a continent roughly the size of the United States and Mexico combined. Flying radar survey lines across all of it takes years and costs enormous amounts of money. The surveys that were completed, mostly from the 1960s onward, covered large areas but left significant gaps. Where surveys were done, the resolution was limited. The spacing between flight lines meant the map had data points every several kilometers, with the terrain between them essentially interpolated rather than measured. The result was a map that captured the broad outlines of the subglacial landscape but missed the medium-scale features, the valleys, ridges, canyons, and basins that are too small to appear in coarsely spaced radar surveys, but large enough to matter significantly for how the ice flows over them. The best previous attempt at a comprehensive Antarctic bedrock map was a product called BedMachine Antarctica, published in Nature Geoscience in 2019. BedMachine combined radar survey data from multiple decades and multiple nations with a key innovation. It used the physics of ice flow to fill in the gaps between survey lines. Instead of simply interpolating between data points, BedMachine used the known conservation of ice mass, the principle that the volume of ice entering a section of glacier must equal the volume leaving it, accounting for melting and accumulation, to constrain what the bedrock must look like in areas with no direct radar measurement. BedMachine was a significant improvement over everything before it, but it still had limits, particularly at the medium scales between 2 and 30 kilometers, where many of the features most relevant to glacier behavior exist. The January 2026 study, published in Science on January 15th, and led by Dr. Helen Ockenden of the University of Grenoble-Alpes, addressed that gap with a fundamentally different approach. The technique is called Ice Flow Perturbation Analysis, or IFPA. The core principle behind it is that the surface of the ice sheet is not perfectly smooth. Beneath the apparently uniform white surface, the ice undulates in subtle ways, gentle rises and dips in the surface elevation that are caused by variations in the bedrock below. When ice flows over a ridge, it rises slightly. When it flows over a depression, it sinks slightly. The surface expression of these perturbations is extremely small. A 100-meter deep canyon in the bedrock, as researcher Robert Bingham noted, causes the ice surface above it to dip by only a tiny amount, nearly invisible to the naked eye. But it is detectable by satellite altimetry, the same kind of precise surface height measurement that Cryosat-2 uses to track subglacial lake activity. EFPA takes that principle and applies it systematically. By analyzing how the ice surface warps as it flows over hidden obstacles, and using the physics of ice deformation to decode those surface signals backward into bedrock features, IFPA can produce a map of the hidden terrain at a resolution and coverage that airborne radar surveys alone cannot match. Ockenden described the difference in practical terms. It is like going from a grainy, low-resolution camera to a properly zoomed-in digital image of what is actually there. What that digital image showed, when applied to Antarctica, was extraordinary. The most striking single discovery in the January 2026 study was a massive hidden trench carved into the Maud subglacial basin in East Antarctica. The trench stretches nearly 400 kilometers, roughly the distance by road from London to Newcastle, or from New York to Boston and back. It is not a narrow crack. It is a substantial geological depression carved into the bedrock by ancient water flow, existing entirely beneath the ice sheet, with no surface expression that any previous survey had clearly resolved. The trench predates the modern ice sheet, meaning it was formed when Antarctica was a different place, warmer, partly or fully ice-free, with liquid water flowing across its surface, carving channels into the rock exactly as rivers carve valleys everywhere else on Earth. The other features revealed by the study ranged in size from 2 to 30 kilometers, the mesoscale range that previous mapping techniques had consistently under-resolved. Valleys, plains, basins, ridges, Ancient riverbeds. These features act, in Ockendon's description, as the primary gears and brakes of the ice sheet. The hidden ridges slow ice flow, where the ice has to push over them. The hidden valleys channel ice flow into faster-moving streams. The hidden basins create the conditions where subglacial lakes form and persist. The bedrock landscape that no one could previously see clearly is the fundamental architecture controlling how the ice above it behaves. Duncan Young, a researcher who wrote a perspective piece accompanying the study in Science, noted that while the new map represents a major advance, it does not represent the final word on Antarctic geography. The IFPA technique resolves features down to a certain scale, but still cannot capture the finest details of bedrock topography. What it provides is a stable, high-resolution foundation for climate models, allowing scientists to incorporate realistic bedrock geometry into their projections of where ice is most vulnerable and how fast it will retreat. The Gamburtsev subglacial mountains deserve specific attention because they represent one of the most geologically puzzling features on Earth. Sitting in central East Antarctica, directly beneath the highest point of the ice sheet, the Gamburtsev Mountains are a complete alpine range. Peaks, ridges, carved valleys, the full topographic character of a major mountain system, buried entirely under the ice. Nothing breaks the surface. There is no visible sign at the surface that a mountain range is down there at all. The elevation differences within the range reach approximately 500 meters, making them comparable in scale to the Appalachian Mountains running along the eastern United States. The Gamburtsevs were first detected through airborne radar surveys in the 1950s by Soviet researchers, but their full character, the extent of their peaks and the depth of the valleys carved between them, was not established until subsequent surveys and the improved mapping techniques of the 2000s and 2000s. What makes the Gamburtsevs geologically puzzling is that mountain ranges are formed by tectonic collision, continental plates pushing together and crumpling the crust upward. East Antarctica is one of the oldest and most geologically stable pieces of crust on Earth. It has not been subject to significant tectonic activity for hundreds of millions of years. The Gamburtsev Mountains should not exist under the current geological framework for that region. The leading explanation, still debated, involves a much older period of tectonic activity, possibly more than 500 million years ago, that built the mountains, followed by later erosion that was then interrupted when the ice sheet formed and preserved what remained. The ice, in effect, froze the mountains in place before erosion could finish the job. Also hidden under the Antarctic ice is the deepest land canyon on Earth. The Denman Glacier Trough, located in East Antarctica, descends to approximately 3,500 meters below sea level, deeper than any other canyon on the exposed surface of any continent. It is deeper than the deepest point of the Grand Canyon by more than 2 kilometers. The canyon sits under the Denman Glacier, a relatively unstudied glacier in East Antarctica that has recently attracted scientific attention because its geometry, a deep trough sloping inland below sea level, gives it vulnerabilities similar to those of Thwaites in West Antarctica. If ocean water finds a pathway into the Denman Trough, the same self-reinforcing retreat dynamic that threatens Thwaites could potentially apply there as well. The January 2026 study matters for a specific, practical reason that goes beyond scientific curiosity about what the bedrock looks like. Every climate model that projects Antarctica's future contribution to sea level rise requires an accurate representation of the bedrock as a boundary condition, the fixed landscape that ice flows over, around, and against. If that boundary condition is wrong, if the model thinks the ice is flowing over a flat plain when it is actually flowing through a valley that channels it faster toward the sea, the projection will be wrong. The better the bedrock map, the more accurate the sea level projections. The January 2026 study improved that foundation significantly, and the researchers explicitly framed it that way. More accurate projections reduce the guesswork in planning for coastal adaptation. What the combined body of Antarctic bedrock research has established is a continent with an interior geography as complex and varied as anything on the surface of any other landmass. Mountains, canyons, plains, basins, and rivers. All of it invisible, all of it actively shaping what happens to the ice above it, and most of it discovered within the past 2 decades, as technology finally developed to the point where seeing through kilometers of ice became possible. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. But the hidden geology of Antarctica is not only about what is under the ice now. The bedrock in those ancient valleys and mountains preserves something else, a physical record of what Antarctica used to be, fossilized in the rock exposed at the continent's edges, and preserved in the layers of ice above the valleys the 2026 study mapped, is evidence of a continent that was once so different from what it is today that it would be almost unrecognizable to anyone looking at a modern map. Section 8. Antarctica's ancient tropical past. The fossils under the ice. The continent that exists today, white, frozen, hostile to almost all complex life, with interior temperatures dropping below -60 degrees Celsius in winter, has not always been this way. What Antarctica was for most of its geological history is so different from what it is now that understanding the transition between those two states is one of the most important questions in Earth science. The fossils that have been pulled from the rock at its edges, the plant remains preserved in ancient sediment layers, and the ice cores drilled from its interior all tell the same story. This was once a warm, forested, biologically rich continent, and the process by which it became a frozen desert is directly relevant to what is happening to it right now. Start 540 million years ago, before any of the modern continents existed in their current positions. Antarctica was part of a massive ancient supercontinent called Gondwana, a landmass that also contained what would eventually become South America, Africa, India, Australia, Madagascar, and New Zealand. Gondwana itself was assembled from even older continental fragments and existed for hundreds of millions of years before it began to break apart. Throughout most of this time, the area that would become Antarctica occupied various positions on the globe, not always at the South Pole. The geological evidence shows it moving gradually toward its current polar position over an enormous span of time. But even once it was at the pole, it was not initially frozen, because the conditions that produce an ice sheet require not just polar positioning, but also the right atmospheric chemistry and the right oceanic circulation, neither of which existed in their current form for most of Earth's history. The first piece of fossil evidence that Antarctica was once biologically rich came from the continent's own rock, exposed at the edges of the ice sheet and in the trans-Antarctic mountains. The most famous early discovery was Glossopteris, a seed fern plant that grew across Gondwana during the Permian period, roughly 252 to 299 million years ago. Glossopteris fossils have been found in Antarctica, South Africa, India, South America, and Australia. Their presence on all of those land masses, which are now separated by thousands of kilometers of ocean, was one of the key pieces of physical evidence that convinced geologists in the early 20th century that these continents had once been joined. The Antarctic Glossopteris fossils were found in circumstances that remain one of the more striking moments in the history of polar exploration. In 1912, Robert Falcon Scott and his team reached the South Pole, only to discover that Norwegian explorer Roald Amundsen had beaten them there by 34 days. On the return journey, Scott's party was collecting geological samples from the Beardmore Glacier area. They were already weakened, already behind schedule, already facing the conditions that would kill all 5 of them before they could reach their base camp. They were carrying 16 kilograms of rock specimens with them anyway. When the rescue party found Scott's tent 8 months later, those specimens were still there beside the bodies. The fossils in them included Glossopteris, plant life from a Gondwana forest that had grown in Antarctica approximately 250 million years earlier. Scott's team died carrying evidence that Antarctica had once been warm. Lystrosaurus is another fossil find that ties Antarctica directly into the Gondwana story. Lystrosaurus was a mammal-like reptile, technically a dicynodont therapsid, that lived during the early Triassic period, roughly 250 million years ago, shortly after the largest mass extinction in Earth's history wiped out approximately 90% of all species. Lystrosaurus survived that extinction and became extraordinarily abundant in the aftermath. Its fossils have been found in Antarctica, South Africa, India, and China. The Antarctic specimens, discovered in the trans-Antarctic mountains, matched the South African and Indian ones closely enough to confirm that these animals had walked across land connections between those regions, connections that only existed because the continents were then part of the same landmass. Moving forward in geological time to approximately 190 million years ago, the early Jurassic period, Antarctica was still connected to the other Gondwana fragments, still at a southern but not yet polar latitude in terms of climate behavior, and still warm enough to support forests and large animals. This is the period that produced the most famous Antarctic dinosaur. Cryolophosaurus elioti was discovered in 1991 by paleontologist William Hammer and his team working in the Beardmore Glacier region of the Trans-Antarctic Mountains. The specimen was found at an elevation of approximately 4,000 meters, in rock that had to be approached by helicopter and worked in temperatures that made extended excavation extremely difficult. Cryolophosaurus was a theropod, a bipedal predatory dinosaur in the same broad category as Tyrannosaurus rex, though much earlier and on a different evolutionary branch. It measured approximately 6 to 6.5 meters in length. What made it immediately distinctive when researchers analyzed the skull was the crest sitting on top of its head, a bony, forward-curving projection running perpendicular to the length of the skull, unlike the crests of any other known theropod. The name Cryolophosaurus means frozen crested lizard. Researchers nicknamed it Elvisaurus. The crest bore an accidental resemblance to a pompadour hairstyle. The formal nickname that stuck in popular coverage was the cold-crested killer, though the animal lived in a climate far warmer than modern Antarctica. The same excavation that produced Cryolophosaurus also found remains of a sauropodomorph, a long-necked herbivorous dinosaur related to the animals that would eventually evolve into the giant sauropods like Brachiosaurus and Diplodocus. Finding both a predator and an herbivore in the same Antarctic deposit confirmed that the ecosystem of early Jurassic Antarctica was not marginal or impoverished. There were animals large enough to need large prey. The food chain was functioning. The continent supported the same kind of complex terrestrial ecosystem that existed elsewhere in the world at the same time. Marine reptile fossils have also been recovered from Antarctic rocks. Mosasaur specimens, large predatory marine lizards that ruled the oceans of the late Cretaceous period, have been found in sedimentary rock along the Antarctic peninsula. These animals were not dinosaurs, but were contemporaries of the last dinosaurs, swimming in the seas that surrounded Antarctica when the continent was still warm enough to have open, biologically rich coastal waters. Their presence in Antarctic marine sediments confirms that the seas around the continent were warm and productive, right up until the conditions that produced the modern ice sheet began to take hold. The transition from warm, forested continent to frozen desert was not instantaneous. It was a gradual process driven by two interacting factors: the breakup of Gondwana and the opening of a critical oceanic passage. Gondwana began fragmenting during the Jurassic period. South America, Africa, India, and Australia progressively separated and drifted northward. Antarctica remained connected to South America the longest. The critical moment came approximately 30 to 35 million years ago, during the Eocene-Oligocene transition, when the final land connection between Antarctica and South America broke apart and the Drake Passage, the body of water between the southern tip of South America and the Antarctic Peninsula, opened fully. That opening allowed the Antarctic Circumpolar Current to establish itself for the first time. The Antarctic Circumpolar Current is the largest ocean current on Earth. It flows continuously eastward around Antarctica, driven by westerly winds, and because it encircles the continent without any land barriers interrupting it, it forms a thermal wall. Warm ocean water from the Atlantic, Pacific, and Indian Oceans cannot easily cross the current to reach Antarctica's shores. The continent was effectively cut off from the warming influence of the global ocean circulation. Combined with decreasing atmospheric carbon dioxide levels during this period, the thermal isolation produced by the circumpolar current drove Antarctica's temperatures down enough for permanent ice to begin accumulating. The ice sheet that exists today started forming roughly 34 million years ago and has remained, with some variation in extent during warmer and cooler geological periods, ever since. The ice that began forming 34 million years ago has been doing something ever since that makes it one of the most valuable scientific archives on Earth, preserving the atmosphere. When snow falls in Antarctica, it traps tiny bubbles of the air surrounding it. As more snow falls on top, the layers below are compressed into ice. The bubbles of air are compressed with them, sealed inside the ice. Over thousands and hundreds of thousands of years, layer upon layer of ice builds up, each layer containing a sample of the atmosphere from the year it fell. Temperature can be reconstructed from the ratio of oxygen isotopes in the ice itself. Greenhouse gas concentrations, carbon dioxide, methane, can be measured directly from the trapped air bubbles. Dust levels, volcanic ash layers, and even traces of ancient wildfires are all preserved in the sequence. The deepest and most complete ice core record in the world comes from the Epica Dome C site in East Antarctica, drilled by the European Project for Ice Coring in Antarctica. The core drilled at Dome C extends to 3,270 meters below the surface and contains a continuous, unbroken climate record stretching back approximately 800,000 years, covering 8 complete glacial cycles, meaning 8 full repetitions of the Earth's shift from warm interglacial conditions into an ice age and back out again. What that record shows is a direct, consistent relationship between atmospheric greenhouse gas concentrations and global temperature over 800,000 years. When carbon dioxide levels in the atmosphere were higher, temperatures were warmer. When they fell, temperatures dropped and ice ages followed. The 8 glacial cycles visible in the Dome Sea core track that relationship with a regularity that leaves no serious scientific doubt about the mechanism. The core also established the range within which carbon dioxide concentrations had naturally varied over those 800,000 years. Between approximately 180 parts per million during the coldest glacial periods and approximately 280 parts per million during the warmest interglacials. Current atmospheric carbon dioxide concentration, as of 2025, exceeds 420 parts per million. That is higher than at any point in the 800,000-year record preserved in the Dome Sea core. It is almost certainly higher than at any point in the last 3 million years, based on less direct geological evidence extending the record further back. The ice core does not tell you what will happen next. It tells you what happened every other time in the past 800,000 years when the conditions changed in particular directions. That information is exactly what climate models are built on. Beyond Dome Sea, the Epica project also drilled a second core at Conan Station in Drawning Maud Land, and multiple other deep ice cores have been drilled at sites including Vostok, Taylor Dome, and the West Antarctic Ice Sheet Divide. Each core adds resolution to the climate record and allows researchers to cross-check their findings. The Waste Divide core, completed in 2011 by an American team, provided exceptionally high time resolution for the past 68,000 years, fine enough to study climate changes that occurred over decades rather than centuries. It confirmed that some major climate shifts in the past happened extremely rapidly by geological standards, within decades, rather than gradually over thousands of years. What the fossils and the ice cores together establish is a continent with an extremely long and complex biological and climatic history, most of which is invisible to the casual observer looking at its white surface. The dinosaurs that walked its forests 190 million years ago, the marine reptiles that swam its warm coastal seas, the ancient plants whose remains Scott carried to his death, and the 800,000 years of atmospheric chemistry preserved layer by layer in the ice. All of it exists on the same piece of rock, now buried under the ice sheet that formed when the conditions finally aligned to freeze it. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. The fossils tell you what Antarctica lost. The ice cores tell you what it has been recording ever since. But underneath the ice, sealed in water that has been sitting in complete darkness for even longer than the ice cores can reach, something survived the entire transition. Life that adapted to conditions so extreme that it offers a direct comparison to the questions scientists are now asking about other worlds entirely. Section 9. Life sealed under the ice for millennia. The Mercer Lake discovery. The question of whether life can exist without sunlight, without connection to the surface world, and without the warmth of a star, has been asked by scientists for decades, in theoretical terms. Antarctica answered it, not with a single discovery, but with a sequence of findings, each one building on the last, that collectively establish something that fundamentally changes how biologists think about the minimum conditions required for life to exist. The most recent and most detailed of those findings was published in August 2025. What it revealed about organisms living in complete isolation beneath more than a kilometer of Antarctic ice has implications that reach far beyond the continent itself. To understand what was found, you need to understand the environment where it was found. Mercer Subglacial Lake sits in West Antarctica, beneath the Whillans Ice Stream, a fast-moving section of the West Antarctic ice sheet that flows toward the Ross Ice Shelf. The lake is sealed under 1,085 meters of ice. Above it, the ice sheet moves continuously, grinding and pressing downward. Below it is bedrock. The lake itself occupies the space between, kept liquid by a combination of geothermal heat rising from the Earth's interior and frictional heat generated by the ice grinding above it. The water in Mercer Subglacial Lake has had no contact with the surface atmosphere for a period that researchers estimate in the range of thousands to tens of thousands of years. No sunlight has reached it. No wind has touched it. For all practical purposes, It is a completely closed system, sealed, pressurized, and dark. The Subglacial Antarctic Lake Scientific Access Project, known as SALSA, was an international research collaboration funded primarily by the U.S. National Science Foundation and led by Professor John Priscu of Montana State University and the Desert Research Institute. The collaboration brought together researchers from Montana State, the University of Florida, the Korea Polar Research Institute, and other institutions. Their goal was to reach Mercer Subglacial Lake, collect water and sediment samples without contaminating the system with surface organisms, and determine what was living down there. The contamination problem is not a minor technical detail. It is the central scientific and logistical challenge of the entire enterprise. If you drill through a kilometer of ice and the drill, the water used in drilling, or the sampling equipment carries surface microorganisms down with it, you cannot distinguish what you find at the lake from what you brought with you. The samples become useless. The scientific conclusions become impossible to draw. Getting clean samples from a subglacial lake requires sterilizing every piece of equipment that will contact the water, sterilizing the drill water itself, and maintaining that sterility through the entire process in field conditions at the bottom of the world. The SALSA team used a hot water drilling system, a method that melts the ice by pumping hot water down a hose, creating a hole wide enough to lower sampling equipment through. The water used in drilling was treated by ultraviolet radiation and filtration to remove microorganisms before it entered the hole. Every piece of sampling equipment was chemically sterilized. The team drilled through all 1,085 meters of ice during the 2018 to 2019 Antarctic field season. When they confirmed they had reached the lake, they had a limited window before the borehole refroze, time measured in hours, not days. They collected water samples and sediment from the lake floor and brought them to the surface for analysis. The Korea Polar Research Institute's findings from those samples, published in Nature Communications on August 18, 2025, represented the most detailed genomic characterization of a subglacial Antarctic lake microbiome ever produced. The research was led by Dr. Ok-sun Kim of Kopri and involved genomic analysis of 1,374 single-cell amplified genomes, a technique that sequences the DNA of individual cells rather than working from a bulk sample, allowing researchers to identify what specific organisms are present and what metabolic strategies they use. The core finding was stark. Most of the organisms in Mercer Subglacial Lake belong to previously unknown species. They are genetically distinct from anything found in marine environments, surface freshwater environments, or any other sampled ecosystem on Earth. The isolation of the lake, thousands of years with no exchange of genetic material with the outside world, had allowed its microbial communities to diverge along evolutionary pathways that produced organisms with no close relatives anywhere in the currently cataloged tree of life. These were not slightly unusual variants of known species. They were organisms that had been separated from the rest of life on Earth long enough to become something genuinely different. The metabolic strategies these organisms use are directly relevant to understanding what life can run on in the absence of sunlight. On the surface of the Earth, almost all complex food chains trace back to photosynthesis, organisms using sunlight to convert carbon dioxide and water into organic matter that everything else eats. In Mercer Subglacial Lake, sunlight is not available and never has been. The microbial communities cannot photosynthesize. Instead, the SALSA research found two primary metabolic approaches being used in different parts of the lake, organized largely by oxygen concentration. The first approach is heterotrophy, consuming organic matter that already exists. In Mercer Subglacial Lake, the organic matter available to heterotrophic organisms comes primarily from ancient material in the sediments, deposited over long geological timescales and slowly being consumed. Heterotrophs in the lake are essentially living off the accumulated organic legacy of a time when the area was not under ice, eating the biological residue of a warmer world. The second approach, more remarkable, is chemoautotrophy, drawing energy directly from chemical reactions between inorganic compounds rather than from organic matter or sunlight. Chemoautotrophic organisms in Mercer Subglacial Lake use the chemical energy stored in the interactions between water, dissolved minerals, and rock. The bedrock beneath the lake contains sulfur compounds, iron compounds, and other reactive minerals. The organisms capable of exploiting those reactions do not need organic food and do not need light. They need chemistry. They sit at the interface between the water and the rock, oxidizing minerals for energy and building their own organic compounds from scratch using that chemical energy. They are, in a meaningful sense, eating rock. The distinction between the two metabolic strategies in the SALSA dataset was not random. The researchers found that microbial community composition varied systematically with oxygen concentration throughout the lake water. In the better oxygenated portions, heterotrophs and certain chemoautotrophs dominated. In the oxygen-depleted zones closer to the sediment, communities shifted toward organisms that can operate in the near-complete absence of oxygen. Anaerobic chemoautotrophs, drawing energy from sulfate reduction and other anaerobic chemical pathways. The lake was not a uniform environment. It had internal structure, and the organisms in it had partitioned that structure according to their specific capabilities. Professor Priscu, the chief scientist of the SALSA project, described the Mercer Lake ecosystem as a community that has been shaped by long-term isolation into highly specialized forms. The study characterized the microbial population as showing genetic isolation and metabolic complexity, the title phrase of the Nature Communications paper. Both words matter. Genetic isolation because the organisms had diverged significantly from all known relatives. Metabolic complexity because the range of energy harvesting strategies on display was not a simple monoculture of one type of organism, but a structured ecosystem with multiple trophic levels operating on entirely chemical rather than solar energy. The Mercer Lake findings did not occur in isolation. They built directly on the first successful contamination-free subglacial lake access, which happened at Whillans Subglacial Lake in 2013, also in West Antarctica, also drilled by an American team under John Priscu's scientific leadership. The Whillans access was the proof of concept. The team reached the lake, confirmed liquid water, and collected samples that showed microbial life was present and active. The organisms found in Whillans were dominated by round-shaped cells alongside rod-shaped bacteria, spirochetes, and filamentous organisms. Many were actively cycling nitrogen, processing ammonium and nitrite as energy sources in complete darkness. The Whillans discovery established that subglacial Antarctic lakes are not sterile. The Mercer discovery established how deep the biological complexity of those systems goes. These two successful contamination-free accesses, Whillans in 2013 and Mercer in 2018 to 2019, with the full genomic analysis published in 2025, are the only times in human history that scientists have achieved this. The United States research teams involved remain the only groups to have done it. Hundreds of other subglacial lakes in Antarctica have never been sampled. What they contain is genuinely unknown. The astrobiological implications of the Mercer and Whillans findings are the reason NASA and the European Space Agency both pay close attention to Antarctic subglacial lake research. Two bodies in the outer solar system are currently the strongest candidates for extraterrestrial life: Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Europa has a global liquid water ocean estimated to be between 60 and 150 kilometers deep, sealed beneath an ice shell approximately 10 to 30 kilometers thick. The ocean has likely existed for billions of years, kept liquid by tidal heating from Jupiter's immense gravitational pull flexing the moon's interior. Enceladus has a subsurface ocean that is confirmed by direct observation. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, detected plumes of water vapor and ice particles venting through cracks in the moon's south polar ice shell. The plumes contain water, salt, silica particles, organic compounds, and molecular hydrogen, the hydrogen produced by chemical reactions between hot water and rock, the same reaction that chemoautotrophic organisms in Mercer Subglacial Lake exploit for energy. The argument against life in Europa's or Enceladus's oceans has historically rested partly on the absence of sunlight as a deal breaker. If no energy from the sun can reach the water, how could anything live there? Mercer Subglacial Lake answers that argument directly. Life in Mercer does not use sunlight. Life in Whillans does not use sunlight. They use chemistry. If the chemistry is available, reactive minerals, liquid water, dissolved gases, life in Antarctica has demonstrated it can build an entire functioning ecosystem on that foundation alone. Europa and Enceladus have liquid water. Enceladus has the specific chemical signature of water reacting with hot rock. The parallel to subglacial Antarctic lakes is direct enough that NASA's planning documents for future Europa and Enceladus missions explicitly reference Antarctic subglacial lake research as the closest available terrestrial analog. Getting to Mercer Subglacial Lake required drilling through 1,085 meters of ice in Antarctic field conditions, maintaining sterility throughout, and completing the sampling before the borehole refroze, all at a remote location with no road access resupply only by aircraft, and weather that can ground aircraft for days at a time. The difficulty of doing this properly explains why only 2 subglacial lakes have ever been successfully accessed. It also explains why the 400+ other subglacial lakes known to exist beneath Antarctica remain entirely unsampled. Some of them have been isolated far longer than Mercer or Whillans. Lake Vostok, the largest, has been sealed for an estimated 15 to 25 million years. What evolutionary paths the organisms in Vostok have taken over that time frame, if any survived, is completely unknown. Russian researchers drilled into Lake Vostok in 2012, but the contamination controls used have been questioned by the broader scientific community, and the results from that drilling remain scientifically contested. The SALSA project's August 2025 publication represents the current frontier of what is actually known about life under Antarctic ice. It is not speculative. It is not extrapolated from indirect evidence. It is a direct measurement of what exists in a specific lake, obtained through a process that eliminated contamination as an explanation for the results, analyzed using genomic techniques rigorous enough to distinguish previously unknown organisms from known ones. The life in Mercer Subglacial Lake is real, it is complex, it has been there for a very long time, and it does not need the sun. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. What makes the broader subglacial story complete is not just what lives in the lakes, or what the ice above them records, or what the bedrock below them looks like. It is the relationship between all of those things and the question of who is watching and what tools they have built to watch with. The drones that fly over the ice surface, the satellites that measure it from orbit, the autonomous vehicles that swim beneath it, and the regulations that govern all of those activities form a system of surveillance and governance unlike anything else on Earth. Whether that system is adequate for what the continent is now undergoing is the question that brings the entire picture together. Section 10. Drones over Antarctica. What they're actually capturing right now. The image most people carry of Antarctic surveillance is shaped by conspiracy content. Military drones flying over a forbidden zone, capturing footage of something that powerful governments immediately suppress. The reality of how Antarctica is actually being watched right now is more technically sophisticated, more geopolitically complicated, and in its own way, more revealing than any conspiracy version of events. The continent is being monitored from space, from the air, from the surface, and from beneath the ice simultaneously, by multiple nations using a range of technologies that did not exist when the Antarctic Treaty was written. What those technologies are finding, and what the expanding cast of nations trying to access the continent means for the governance system built in 1959, is the actual story of surveillance in Antarctica today. Start with drones, because that is where the title of this episode begins. Unmanned aerial vehicles are being used in Antarctica for legitimate scientific research right now, and what they are collecting is genuinely significant. ABC News documented test flights of a heavy-lift research drone that covered more than 430 miles of Antarctic territory collecting climate data. The specific value of drones in Antarctic research is not mystery hunting. It is the ability to access terrain that is too dangerous or logistically prohibitive for crewed aircraft. Remote glacier surfaces, coastline sections that require low-altitude passes, wildlife colony areas where the presence of a crewed aircraft would cause disturbance that a small UAV can minimize. Drones can carry ice-penetrating instruments, thermal cameras, and atmospheric sensors into locations that would otherwise require expensive and risky crewed expeditions. The regulatory framework governing those flights is specific and enforceable. Under the Antarctic Treaty System's UAV guidelines, no drone can fly over Antarctic specially protected areas without advanced authorization from a national competent authority. No drone can fly over or near concentrations of wildlife, on shore or at sea. No drone can be operated near a scientific station without the explicit permission of the base commander. UAV flights for scientific or commercial purposes require authorization from a relevant national authority before the operation begins. If at any point during a flight, the drone causes observable disturbance to wildlife, if animals show unusual behavior or interest in the aircraft, the flight must be aborted immediately, regardless of what data is still being collected. These rules are not suggestions. They are the terms under which access to the continent is permitted. The enforcement of those rules was demonstrated clearly in June 2025 when Ethan Guo, a 19-year-old pilot attempting to fly solo to all 7 continents, was arrested by Chilean authorities after landing his Cessna on King George Island without authorization. His case was not about drones, but it illustrated the response mechanism that the Antarctic Treaty governance structure triggers when airspace protocols are violated. A Chilean court ordered a 90-day investigation. Guo remained under legal restrictions from both Chile and the Antarctic Treaty system. The sequence of events, unauthorized entry, immediate arrest, formal legal proceedings, is the documented reality of what actually happens when Antarctic airspace rules are broken. The most consequential unmanned vehicle currently deployed in Antarctic research was not a drone flying above the ice, but a submarine operating beneath it. RAN is a 7-meter-long, bright orange autonomous underwater vehicle operated by the University of Gothenburg in Sweden as part of the International Thwaites Glacier Collaboration. In the 2023 to 2024 Antarctic field season, RAN was deployed beneath the Thwaites Glacier ice shelf, swimming under 350 meters of ice to map the underside of the glacier directly. No human-operated submersible can access that environment. The ice overhead makes recovery impossible if anything goes wrong. RAN operated autonomously, following pre-programmed routes beneath the glacier and collecting sonar data from the ice above it and the ocean floor below it. The maps it produced before the end of that deployment were the first detailed maps ever made of the underside of a major Antarctic glacier, showing the geometry of the melt channels, the shape of the cavities where warm ocean water was eating at the ice from below, and the seafloor topography of the region the glacier was retreating over. On February 9, 2024, the ITGC publicly announced that RAN had gone missing in action in West Antarctica. The collaboration described it as a highly valued component of their research program. The vehicle was not recovered. The data it had already transmitted back, however, contributed directly to the September 2024 ITGC consolidated findings on Thwaites retreat. The loss of RAN illustrated something important about the conditions under which Antarctic surveillance actually operates. This is not a controlled environment. Equipment failures, weather events, and the sheer remoteness of the research sites mean that even well-funded, technologically sophisticated programs lose assets. The conspiracy framing of Antarctic surveillance, in which all-seeing military drones fly freely over a perfectly managed, restricted zone, bears no relationship to the practical reality of operating in one of the most hostile and inaccessible environments on Earth. Above the ice, the most comprehensive surveillance of Antarctica is not conducted by aircraft at all. It is conducted by satellites. The European Space Agency's Cryosat-2, operational since 2010, has been the primary tool for tracking changes in Antarctic ice thickness and detecting subglacial lake activity. Its radar altimeter measures ice surface height to centimeter precision from orbit, detecting the millimeter to meter changes that indicate subglacial lakes filling and draining, glaciers accelerating or slowing, and ice shelves thinning or thickening. The 85 subglacial lakes identified in the 2025 Nature Communications study were found using Cryosat-2 data. The fracture development on the Thwaites Eastern Ice Shelf, documented in the December 2025 Journal of Geophysical Research study, used 20 years of satellite and GPS data. The January 2026 Bedrock Mapping study used satellite altimetry as the primary data source for the ice flow perturbation analysis technique. Every major Antarctic discovery in the past decade has satellite data as a central component. NASA's ICESat-2 satellite, launched in September 2018, uses laser pulses rather than radar to measure ice surface height, providing complementary data to Cryosat-2 with different error characteristics. The combination of the two systems allows researchers to cross-check measurements and identify signals that appear in both data sets, the signatures most likely to represent real physical changes rather than instrument artifacts. NASA's Operation Icebridge, a crewed airborne mission that used specially equipped aircraft to bridge the gap between the IceSat satellite that ended in 2009 and IceSat-2's 2018 launch, flew repeated surveys of Antarctic ice for 9 years, building a continuous record of change that connects the older satellite record to the newer one. The surveillance picture from above is therefore not a secret military operation. It is a publicly documented, multi-agency, multinational monitoring system whose data is published in peer-reviewed scientific journals and whose archives are accessible to researchers around the world. The Antarctic sun, the publicly available news publication of the United States Antarctic Program, reports regularly on research conducted using these systems. The treaty's Article 3 requires that scientific observations and results from Antarctica be exchanged and made freely available. The monitoring infrastructure built to watch the continent is operating in direct compliance with that requirement. What is changing in the surveillance picture is not the quality of the technology, but the cast of nations seeking access to the continent. In February 2024, the commander of Iran's regular navy made a formal public statement that Iran claims property rights in Antarctica, plans to raise the Iranian flag on the continent, and is preparing to launch both scientific and military projects there. Iran is not a party to the Antarctic Treaty. It has signed none of the agreements that govern access to the continent and has no legal obligation to honor the restrictions those agreements impose. The statement was not accompanied by immediate action, but it represents exactly the kind of geopolitical pressure that the 1959 treaty system was not designed to handle. A major regional military power with no treaty obligations, declaring its intention to operate on the continent on its own terms. Iran is not the only non-signatory with expressed Antarctic interest. The treaty currently has 58 member nations. There are nearly 200 countries in the world. The governance of Antarctica depends on the agreement's legitimacy being accepted by nations that were not part of the original 1959 negotiation and whose interests were not represented in the Cold War framework that produced the treaty. As Antarctic resources, freshwater, potential mineral deposits, fisheries in the surrounding Southern Ocean become more valuable in a warming world, the pressure on non-signatory nations to either join the treaty or disregard it is only increasing. The 46th Antarctic Treaty Consultative Meeting, held in Kochi, India in May 2024, included discussions on tourism management, a topic that has grown from a minor agenda item to a significant governance challenge over the past 2 decades. Tourism to Antarctica has expanded dramatically. The International Association of Antarctica Tour Operators reported that in the 2022 to 2023 season, more than 100,000 tourists visited Antarctica, a number that would have been unimaginable when the treaty was written. The ATCM has repeatedly discussed how to manage that traffic without degrading the ecosystems the treaty is designed to protect, and in 2022, adopted a resolution preventing the construction of any structure or facility exclusively for tourism purposes intended to operate in Antarctica over multiple seasons. The question of enforcement, how the treaty system actually prevents a tourist operation from a non-compliant operator registered in a non-signatory nation, remains unresolved. The Royal New Zealand Air Force has conducted regular patrol flights from Pegasus Airfield near McMurdo Station since January 2006, when a trial flight by a P-3K Orion Maritime Patrol aircraft confirmed the feasibility of conducting such patrols in support of the Convention for the Conservation of Antarctic Marine Living Resources. Those flights watched the Southern Ocean for illegal fishing, vessels taking toothfish, krill, and other species in violation of the conservation limits set under the treaty system. Illegal, unreported, and unregulated fishing in the Southern Ocean is a documented and ongoing problem. The patrols of the enforcement mechanism and their effectiveness is directly limited by the coverage area and flight frequency that New Zealand can sustain. What all of these surveillance systems, the satellites, the AUVs, the patrol aircraft, the research drones, are actually capturing is a continent in rapid transition. The ice is moving faster than the models predicted. The subglacial lakes are more numerous and more dynamic than the models assumed. The bedrock beneath the ice is more complex than the models incorporated. The volcanoes beneath the ice are more numerous than anyone knew. The life sealed in the subglacial lakes is more biologically rich than anyone expected. Every major finding of the past decade has been a revision in the same direction. Things are changing faster, and the systems involved are more complex than the previous generation of research had established. The drones flying over Antarctica right now are not capturing footage of suppressed ancient civilizations or alien infrastructure. They are capturing a continent that is melting, cracking, and shifting in real time, watched by instruments that generate hundreds of terabytes of data per year, analyzed by researchers whose findings are published openly, and governed by a legal framework that is being strained by geopolitical forces its architects did not anticipate. The genuine story of what is being found in Antarctica, the hidden lakes, the buried volcanoes, the fracturing glaciers, the ancient life sealed under the ice, the 800,000-year atmospheric record, the subglacial mountains nobody knew were there, is not a secret. It is published in Nature, in Science, in the Proceedings of the National Academy of Sciences, in the Journal of Geophysical Research. The reason it feels like a secret is not suppression, it is attention. The real findings are technically dense, take years to produce, and arrive without the production value of a leaked drone video. The conspiracy version is immediate, dramatic, and designed to feel like forbidden knowledge. One of those two versions of Antarctica will determine what the public understands about the most consequential piece of geography on Earth for the future of global sea levels, atmospheric chemistry, and the conditions that make coastal cities habitable. The version built on verified research is the one worth knowing. If you enjoyed this video, make sure to subscribe. Thanks for watching, and I'll see you in the next one.